2 more minutes. From that side, some of you will time this side. Some of you can come this side. Because of the videos, she will be mostly restricted to this. Okay. So, friends, good afternoon. We are happy that Dr. Smruti Bulsari is with us. So, she actually challenges herself. I can put it. She taught at Surat, Veer University in the management department, and then in the human resources, and then suddenly she left all that and she thought that she should get into data science, and she did some data science, and then she taught elsewhere here and there, including Meghna Desai School of Policy in Mumbai, and now currently she is at Essex with the Business and Government Data Research Center. So they are doing some interesting work. We happen to I happen to know her mentor long back, and then in some context when we got in touch with him a couple of years ago, he suggested, no, she is the person for R and data. So they have a very interesting book. I don't know how many of you have been statistical analysis in simple steps with R. So it's an online platform also is there for people who teach and learn. So, Dr. Bulsari, the platform is yours, and welcome again to IGIDR.
Thank you very much. Thank you very much, Srijit, for the generous introduction, and thank you for giving me this opportunity to discuss and learn, because today at the end of the session, you will learn something, I'll learn something. And of course, to listen to my guru for 1 hour. Today, do I really need a mic, or is it for the
Recording?
Oh yeah, okay.
I'm just waiting for your pointer.
All right, so the topic, as you can see, is employing big data analytics in economics. I was having some informal discussions before the session began, and there were questions about what exactly big data is. The answer is very simple. It is just big. Yeah. So it is just data which is voluminous, which is bulky, and if you talk in terms of IT language, it is in terms of much more than gigabytes. It could be petabytes and zettabytes of data. Of course, a simple computer or a laptop which I use, Mine is actually a very high-end laptop, but still it takes its own time to process even several megabytes of data. So let apart gigabytes or zettabytes. So you need a GPU and plugging systems. You have to have a pool of systems and stuff. You have to have high-end servers to run those programs and so on. And that is what makes it big. That is one aspect of big, is the volume. Second aspect of big is the velocity. Again, today we had a discussion on what is the difference between AI and machine learning, or what is the difference between AI and big data analytics. So my answer is, when you talk about AI, velocity is important. But if you talk only about machine learning, velocity is not important. You can have static data, you can have data on your hard disk, you can have data on your server, and you can access the data. But if it is AI, it has to be continuous supply of data. So that is one major difference. The algorithms remain the same, but velocity is also important when you talk about big data, and especially applications in AI. If it is just machine learning, velocity may not be important depending upon your research question, or depending upon what you're trying to do with your machine learning algorithms. So with this background of big, I move forward to my today's talk outline. I'll begin with the discussion on what is the difference between statistics. I would rather say statistics oblique econometrics and data science. Today I was discussing with some of the students, and they had precisely the same question, that what exactly is the difference between econometrics and data science. So that is where I thought I should begin my session with. And yeah, one very, very important thing that I would like to emphasize is data science is not a replacement of statistics. Data science makes use of statistics. Data science makes use of mathematics. So mathematics and statistics are not redundant. Econometrics is not redundant. All these things have very strong scientific base. They are never going to get redundant. Just the approach changes when we talk about data science. So data science is not completely new. Leave away statistics, leave away econometrics. No, that is not the thing. It has to be in the base. I think the second part I already started a bit about it, but I'll talk more in detail about big data and big data sources. Then a quick slide on applications of data science in economics, where I present some examples where data science can be applied to economics problems. And then there is an interesting paper by Varian, where he talks about, where he challenges, in fact, one of the published papers by Munell and others, who argue that people, people who are black. So typically we talk about Africans. So Africans are being kind of discriminated when it comes to giving the mortgage for housing. Varian basically challenges that, and he comes up with completely different results when he applies data science techniques, and that is what I'm going to discuss next. A quick overview, because I mentioned Varian's paper and the methods used by Varian in his paper. We have to have some idea about what is supervised learning and unsupervised learning. So these are two main methods of machine learning, or two classifications in which machine learning algorithms are categorized. So I'll have a brief discussion on what is supervised learning and what is unsupervised learning. And then I think I plan to devote a larger time on my ongoing research. And my ongoing research, which I'm going to show it to you today, you may start applying your minds right away from the slide 1. There are some issues with the outputs. I'm clearly aware about what the issues are. I also have the solution. I just have to write the code to sort out those issues. But despite the issues, it still gives us some important insights. So I would like to discuss with you about those insights, as well as I would like to know from you what you think about the loopholes that are there in the system. Sorry, in the algorithm. And before I begin my session, I always tell that if you have any questions in between, just interrupt me. Don't wait till the end. We might have question answer slot in the end, but I would prefer that you would stop me then and there and then ask the question and clarify it. Because sometimes XYZ may have a doubt, she might have a doubt, she might ask a question and he might think that, oh, I had the same question in my mind. So I would prefer people asking questions as you go. So coming to statistics versus data science. Statistics is the base, can't do without it. But if you talk about the basics, the approach, the difference in the approach is that statistics invariably we begin with descriptive statistics, we begin with graphs. Here also we begin with descriptive statistics, we begin with graphs, but we begin with slightly advanced kind of graphs. We begin with more than two-dimensional graphs. Sometimes two-dimensional graphs are also enough. You don't have to have more than 2 dimensions always. You can still have a simple bar graph and call it a data science graph, a data science chart. But yeah, you can have more complex visualizations with the data science tools. You have packages in R, you have packages in Python to develop visualizations. I personally prefer R for visualizations and Python for machine learning. So yeah, R is a very useful software. If you're doing statistics, R is really, really good. I strongly recommend R. But if you're thinking of machine learning, there are ready libraries available. There are libraries available even in R. But if you are using Python, you will find that Python codes are far more efficient because they are written in C, C++. Not all R programs are written in C, C++. Initial base module and some of the modules are written in C, C++. And then most of the libraries in R are written in R itself. So this is what makes Python more efficient. And when you are using when you are using machine learning techniques, Python would you will find Python more efficient. Okay, so coming back to statistics and data science. So we begin with descriptive statistics and visualizations, whether it is statistics or data science. We need to understand data. That is the first thing. Whether it's a data science project or a simple statistical model that we are trying to develop, we need to understand data, and therefore we need to have descriptive statistics and visualizations, or graphs, whatever you may call it. Visualizations is slightly more than graphs. It is not just graphs, it is more than graphs. You have more complicated and, as I said, higher dimensional graphs as well. But then, as you proceed further, in statistics, you either try to examine associations or you try to examine differences. Slightly further, if you talk about associations, you try to see cause-effect relationship. That is a regression. It could be linear regression, it could be non-linear regression, it could be logistic regression, it could be any XYZ regression, but a regression ultimately. So anything that is other than t-test, ANOVA is also one kind of regression actually. But talking about associations and cause effects, we talk about regressions. Data science, we talk about regression as well. And that is the base. That is the statistics in data science. But now what is the basic difference? The approach in statistics is you begin with the hypothesis. Right. On the basis of hypothesis, you identify what are your dependent variables and what are your predictors or independent variables. You have some a priori theory in mind. So you take that theory as the base. And then, keeping that theory in mind, you want to test using your data whether the data conforms to the theory or not. That is statistics. The approach in data science is completely different. You are still using regression, you are still using the same model, but you do not begin with a hypothesis. You only want to know what is your outcome variable. No, thank you. I just had coffee. Okay. So in data science, you are interested in the outcome variable. We typically use the term outcome variable because we are interested in the outcome. So outcome variable is identified, and then everything else, literally everything else goes as predictors. Now, since you people are trained in econometrics, you will ask me that this would pose a multicollinearity problem. If everything goes as predictors, it could result in multicollinearity problem. That is not our problem. That is not the problem of a data scientist. That algorithm will take care of. Algorithm will keep those variables out. And algorithms will do far more efficiently on the basis of data, not on the basis of theory. We are more efficient when we are using the theory in the background. But if you are not using the theory in the background, algorithms are far more efficient. So this is the major difference between statistics and data science, that you begin with a hypothesis in statistics or econometrics. You have to have your domain knowledge, whereas in case of data science, you may or may not have the domain knowledge. I personally believe that it is good to have domain knowledge because that will help you in identifying if there are any issues with the data. I would like to share one of my experiences where we received a data set, and if you are aware, in UK, the GDPR rights are very stringent, the data protection rights. So unlike India, when we collect data using survey techniques, we go with a questionnaire. Hey, what is your name? What is your age? What is your gender? What is this? What is that? And then everything is put in a file. And then we are hardly bothered about the name and address. We make use of all other variables, but our data still contains the name and address, so the person is identified. If she has done a survey and Srijit is using the data, you can approach her and ask who this person is, and he would be able to identify the person on the basis of whatever data is available. Somehow, that is completely not acceptable in UK as per the GDPR regulations. So whatever data you get is normally anonymized. When I say normally anonymized, it does not mean sometimes not anonymized. It is always anonymized, but sometimes even encrypted. You have anonymized unencrypted data, or you have anonymized encrypted data, and then they send the encryption code and you have to decrypt the data. Or sometimes we send them the encryption code, and then we know that we had sent this code and we decrypt the data. So that is how we work on with data. We don't know whose data it is, whether it is a male or a female. Sometimes when gender is important, yeah, you have the gender column, but when gender is not important, don't have the gender column. Whatever columns, I mean, are only the columns that are relevant to what they want us to examine. But then, how to know that a particular attribute or characteristic belongs to a particular person? So when the data is anonymized, some codes are given. Now, when I got the data, there were too many missing values. So the first thing, and yeah, I'm taking a bit of detour over here, where we have a joke among the data scientists. We say that 90% of our time goes in cleaning the data and 10% goes in modeling. So while we were cleaning the data, we saw that there are amazing number of missing values. And some missing values were in columns ABC, some missing values were in column ES, some missing values. So it was kind of, excuse me, मुझे दोनों ही नहीं चाहिए, चाय कॉफी दोनों नहीं चाहिए थे मैंने कॉफी पी लिया ऑलरेडी. Thank you so much. Yeah. So the first blunder that we did was to remove all the rows that were blank. The second blunder that we did, we removed all the columns that were blank. But that didn't turn out to be a blunder, only the rows that we deleted turned out to be a blunder. The person who was supplying the data did not know how to merge the tables. The data was extracted from 4 or 5 different tables, and she did not know how to merge the tables. So first 3 rows belong to first 3 people, and then the next 3 or 4 rows, the next 3 or 4 columns, sorry, the first 3 columns belong to, I'm confusing you. First 3 rows for 3 people and 3 columns were having values. Then the first 2 rows for the next 2 columns didn't have any values, they were missing values. Then the third row had some information in D, E, and F. And that belonged to some other person. So what I'm trying to tell you is, are you getting me? That the data were not collated properly. Now when data are not collated properly, it is this, first of all, the visualizations would help you, and secondly, it was the domain knowledge that actually came to our rescue. That okay, this column has to be, this row has to be merged with this column, this row, and this row, this data of DEF belongs to this row of ABC. So yeah, domain knowledge, as I said, I personally believe is helpful. But even if you don't have the domain knowledge and you are 100% sure that the data is clean, or somebody with the domain knowledge has already cleaned the data for you, fine. Take the variable of your interest, put everything else in the predictor, and let the algorithm do its job. We'll see how it happens. I have all those examples. Okay. Statistics focuses on past, data science on future. Statistics invariably, when we make use of data and we develop a model, when I say statistics, I mean statistics oblique econometrics. So we are doing basically kind of ex post factor analysis, that what is causing what and what is the impact of age on such and such variable. Or maybe I have taken the example of employment. So let us say how age influences employment and how educational level influences employment. And we look at the coefficients, and that is how we try and explain that if educational level increases by 1 more year, it can have this impact on employment, and so on and so forth. Right? But here we are hardly bothered about the coefficients. So I have coefficients for you people. But we are hardly bothered about the coefficients. What we are bothered about is make a model which has a high predictive power. Our focus is prediction. We are not interested in knowing what is causing what and what is the influence of which on unemployment and stuff. What we are interested is in, given this data fed into the model, what are the chances that the person will be employed? That is what we are interested in. Okay, so it typically focuses on predictions, and therefore I have used the word future, that it looks into future. Now, you might say that even statistical models or econometric models also have forecasting ability. Yes, they do have. But again, we will see that why these models are better. I'm not saying that econometric models are worse in any case, but okay. One question to you is that if you toss a coin once, can you tell me the probability just by tossing the coin once that it would be head or a tail? That is the theoretical probability. But if I'm tossing a coin, can you tell me whether it will be head or tail? But if I repeat this 100 times, there are more and more chances that your prediction would be correct. That is the simple concept over here. When you are developing an econometric model or a statistical model, it is a kind of one-time estimation. Here we are estimating the same model over and over. And that is why the use of the term better or maybe more reliable, I would say. Yeah, so all this we have discussed, that concept of statistics are used in data science. Statistics begins with a hypothesis. Yeah, data science focuses and adopts an exploratory approach. Data science models continuously evolve with more and more data, and parameter tuning is a continuous process. So if you have more data, again, you add it to the model, you revise the model, and then again use it for prediction. Then again you get the actual value for Y. Again you revise the model, again you use the revised model for prediction. And that is another important reason why data science models are more reliable. I'm sorry, I don't want to degrade either statistics or econometrics, because for several years even I have been using the same models of economics, of econometrics and statistics, and I still use it. One of my recent publications uses only a statistical model. So, please. Yes. So I don't see the difference. Yeah. Well, the modeling or prediction can be done using econometric models too. And I don't say that they are bad or they are wrong or they are not relevant. I am not even advocating that data science is better. But at the same time, the approach, I'll come to you, yeah. The approach here is, unlike econometrics, where you begin with a hypothesis, you know that, okay, this are the factors which would influence unemployment. Now, can you tell me consumer expenditure can influence unemployment? Nobody in economics would say that. You would tell me you're talking nonsense. Would you tell me that? Say yes, come on. Yeah, data scientists do talk nonsense at times. So yeah, we do talk nonsense. Why? Because you have, even I have, the basic domain knowledge of economics. But the approach of data science is, don't think what your subject says. Use everything. Use all the data that you have. I think this is a very popular example, and I have quoted it at several places. And a lot of people seem to be knowing as well. It's about a survey that perhaps Walmart did. And they tried to examine the buying patterns of the customers so that they can rearrange the items in their stores to optimize the sales. they found that typically on a weekend, people bought diapers and beers together. Everybody who bought diapers bought beers, and everybody who bought beers, they bought them. Now, if you are using the econometric model, you would never ever arrive at this kind of association. So that is one difference. And the second difference is that, as I said, we repeat the model again and again and again with the same data set, but with different observations. So that makes the model slightly more robust. Have I answered your question? Mm-hmm. Okay, yeah. Yeah, fine. You don't have to agree to everything that I say. But if you think that I have not answered your question, or whatever I have answered is something similar to what you believe, that's absolutely fine. And we can even discuss after the session is over. I don't know whether I have time or not. Yeah, your question.
Depends upon your.
Yeah. I don't think we will have time, but I can take up on emails. Yeah. I can't hear you.
There will be understanding of the
Yes. You don't care. Yeah.
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 But they are wrong.
Yes. Yeah. So yeah, you can say it is similar to that. Yeah. It follows this type of approach. Yeah.
Then where would the understanding come? That relation like that. One.
Okay, I'll show you. We can have coefficients as well. Is that what you are asking?
Yeah, I mean, coefficients are numbers, but how do we explain that?
Oh yeah, that comes later. If you come up with something which your theory doesn't support, or it is something different from what the existing theoretical underpinnings are, then you need to explore further. It is similar to what you only answered in your question about grounded theory and about the qualitative approaches. So yeah, you come up with something that is not acceptable in the theory, not established in the theory, and then you start exploring why this has come. Is something wrong with my model, or is something hidden which I can come up with an explanation? Make sense? No. For a very long time?
One way that I understand is recently there is this discussion. C. Raj has wrote his thesis on Paninian grammar about just solving a puzzle. So, but the conventional grammarians, they were thinking about various ways of solving that puzzle. One is that something is obligatory nitya and something is not obligatory anitya. So what you are saying is anitya. Nothing is obligatory.
Precisely. Precisely. It took me years. I mean, it's not that I could change my mindset in a couple of days or months, or even I used to argue with my teachers that how this is possible, and it took me years to accept this. And I repeat, I still use econometric models. I still use statistics. It's not that I've switched over to data science. Data science is not ultimate thing. It has specific applications. Don't use data science to replace econometrics or to replace statistics. Yeah, so this is unconventional, Anitya, as Okay, then data science makes use of large volumes of data sets, unlike what we use. And we may argue that if you are using an FHS data set or an SSO data set, and yeah, once upon a time, even I thought these are huge data sets, but no, then I saw even bigger than that. And that is what the next slide explains. But yeah, considering the sheer volume of the data set, it is better to have some knowledge about the cloud platforms and making use of AWS or Azure databases to extract that data. So yeah, data, again, unconventional thinking, data is not just numbers. We think, when we talk about data, we think in terms of tables, we think in terms of rows and columns. So no, that is data, but there is much more to data than that. You have text data, and there is a technique called text mining or text analytics. I have explored a little bit of it. I have done some work in text analytics, natural language processing. So these are some of the techniques which make use of text data. People analyze, a lot of information is now available on social media. I was discussing, I can't find her in the audience, or maybe I'm not able to locate her, but yeah, I was discussing with one of the students in the afternoon informally that she's looking at NFHS data set, and there are some gaps in the NFHS data set. So fine, we thought of exploring other data sets which gives theoretical, which gives numerical data. But then why not scrape tweets and see what questions are not being answered by the conventional data sets? Scrape the tweets. And I suggested Twitter because it is easy to access data from Twitter. It is easy to scrape tweets than to scrape websites or website scraping. There are algorithms available. This is you Google, you'll get the algorithm. Tweak the algorithm to suit your need, you will be able to use it. Life is simple because of Google. But that's not the thing. If you extract the data from website, or if you extract the data from Twitter or from whatever, it might have HTML tags, it might have XML tags, it might have this enter, which is also a character. So you have to do cleaning of data and stuff. So considering that, I told her that Twitter data would be relatively easier to extract compared to many other sources of text data. And then if you think of extracting data from Facebook or Instagram or LinkedIn, I have people around me, I would just say some colleagues who work with what is called computer vision, that is image data. They work only with image data. Some work only with videos. Some work only with sounds. And if you are working with qualitative data, if you're collecting qualitative data, if you're doing in-depth interview, conventionally we go for transcription, then we go for content analysis. But if you have some know-how of using how to make use of this sound data, maybe you can do it more easily. There are methods of automating content analysis as well. And in text analytics, it is called topic modeling. It is just a different name. It is called topic modeling. But similarly, it could be done for this sound data as well. So yeah, data includes all these things. And yeah, discuss this. Applications in economics and public policy. So specifically, if you are interested in predicting creditworthiness of a potential borrower, these algorithms, machine learning algorithms, would give you much higher accuracy and much higher, apart from accuracy, a couple of more things. Okay, conventionally again, we say that if you are getting a R-square of 90 plus or 95 plus, it's too good to be true. Here we don't bother about R-square. We bother about accuracy. And we focus on getting as high accuracy as possible. The models that I will show you very shortly have 93% accuracy, 95% accuracy, and no, they are not good. They have to have at least 97, 98% accuracy because you're using it for implementing, you are using it for taking a decision. Yeah. Exactly. That is why. Yeah. That is why it has to be as accurate as possible. Because it would straight away have an implication on the business or profitability or revenue or whatever. And therefore you have to be very, very, very responsible. Yes, yes. Yes. You may call it cost, you may call it interest. Right? You have background in economics, so I leave that to you. Risk assessment and estimating the insurance premium. Now, we all know that, okay, if this is your age, you are in this age bracket, if you have this ailment, if you have this, if you have family history, this is your premium. But who the hell decides the premium? One of the methods of deciding premium, I don't say this is the only method, but one of the methods of deciding how much premium is appropriate is through machine learning algorithms. And yeah, when it comes to optimizing financial portfolio, planning for retirement, how much steady flow of income I should have when I retire, all these things, the models could be used. Okay. This is, you might have seen already that a lot of data is available on government portals. Free, absolutely. Completely in public domain and absolutely, should I say that? Yeah, reliable. At least they are clean data. It's not it's not dirty. It doesn't have you don't have to sit and check that okay there could be errors in entry and stuff. In that very reliable I am saying. So far as measurements are concerned, a lot of debates are going on, and you should be following the debates, and you should be knowing the pros and cons of what data you are using. So yeah, a lot of data, and even they are showing visualizations. You may move the mouse and the visualizations would change and stuff. So yeah, they would help in understanding the impact of policy across different regions. Then machine learning algorithms would help you identify who is more responsive to a particular policy and who is not very happy with the same policy. And yeah, social media analysis also helps in the sentiment analysis, if you might have heard, that can be done through social media data. Coming to this example, where mortgage lending in Boston, whether race had an impact on determining the mortgage approval. And as I mentioned, that one of the studies, okay, let me first explain what the data is. 2380 observations, 2380 observations, not at all a big data. It is absolutely a normal data on which you work, I work, everyone works. Not at all big data. 12 predictors. No, still not big data. But Munnell made use of, Munnell and others, there are 3-4 people, made use of logistic regression, simple statistical logistic regression. And the coefficient of race showed a statistically significant and negative impact for black applicants, which means that if the applicant is a black, it is a higher, there are higher odds of his application getting rejected, his or her application getting rejected. So mortgage approval was discriminatory to blacks. That is what was established by this paper in 1996. Instead of logistic regression, Varian used tree-based estimators. So one of the algorithms that I am using today, in fact, two of them are tree-based estimators. So he made use of tree-based estimators, typically classification tree and random forest. Tree, decision tree, are you aware of? Okay, so there is an entity. It might have two or more outcomes. If this is the outcome, go this way. If this is the outcome, go this way. If this is the outcome, go this way. For each outcome, again, there are two or more outcomes, and then that is how a tree is developed. There are branches. There is a node, and then there are branches, and that will help you in deciding whether the mortgage would be approved or it would not be approved. Now, when you have so many trees for the same purpose, you call it a forest. And since the trees are developed using simple random sampling, they are called random forest. So he made use of classification tree and random forest. And yeah, variable, we call it feature. It's the same thing. Variable and feature are the same thing. If you refer to books written for economists, they would still use the word variable, but if you refer to a pure data science book, it would be feature. So he found that it was neither positive nor negative, but it was insignificant completely. So race did not have any impact on mortgage approval. In fact, it was something else which was negatively linked with mortgage approval, and that is to do with the insurance. Yeah, please. Yes. Mortgage insurance denial was one of the. He has used the same data set, same variables, but instead of logistic regression, he used classification tree, that is decision tree, if you know it that way, and he used random forest. Now, what else did he do? Yeah. Yeah. Continuous data is not important, the volume is more important.
So in case of this data, which is tiny data, I can say.
Yeah, it is tiny data.
So is the method still reliable? Is the big data still reliable?
No. And that is what I am coming to the next slide. What he did additional is he did bootstrapping. He inflated the data. He did bagging and he did boosting. All some forms of inflating the data. The same data you inflated. Now, is it ethical or is it correct to inflate the data this way? The answer is yes. And why? Because what are coefficients ultimately when you talk about regression equation? You are basically talking about averages. And when it comes to averages, if you are applying simple random sampling method to generate more and more data using the existing data, you are essentially giving each and every case an equal chance of being selected. So even when you are inflating the data, your average still remains the same. You are inflating it several times that the average doesn't influence. It is that you are tossing the coin so many times that ultimately the probability comes to 1 by 2. That is what the concept is. So bootstrapping, you might have used, you might perhaps be aware about it. It is simple random sampling with replacement. But when it comes to bagging, it is averaging across the models, averaging the coefficients of the models. You bootstrap the data, develop one model, again bootstrap the data, develop another model, again bootstrap the data, develop third model. On averaging the coefficients. In case of boosting, this is even stricter. That with each repetition, the misclassified cases are given more and more weight. Which means that if a case is misclassified, now what is misclassification? There are true values. In the data set, you know that this person has been, the mortgage for this person is approved, mortgage for this person is not approved. Now, when you run an algorithm and the algorithm predicts, if it predicts approved for approved, it is correct. If it predicts not approved for not approved, it is correct. But if it predicts approved for not approved and vice versa, it is a misclassification. And every time there is a misclassification, the misclassification is penalized. It is punished. It is punished so that the algorithm next time knows that this particular case was punished, it has been penalized and therefore penalized, and therefore I have to classify it correctly. So again, in the second iteration, if it still gets misclassified, it's penalized with a higher penalty. Again with a higher penalty, and at some point the algorithm would know that no, I have to take it for approval. So that is.
So in case of this data,
Not 2,380. Now it's much more. And then you divide it into train and test. Well, I'm coming to train and test. You divide the data into train and test. That is one approach for testing. And then there is another approach which is called cross-validation, which means you are testing the same algorithm also again and again. In case of training and test, you are testing it once with some proportion of the original data. But in case of cross-validation, you are testing also again and again and again. Okay? Oh, all right. Okay. And his findings remain the same even after bootstrapping, bagging, and boosting. Now coming to the methods, unsupervised learning and supervised learning. Now when we talk about classification trees, when we talk about random forests, we know that there are classes. The classes are given labels, approved, not approved. So when you are having classes which have clear-cut labels, it could be more than 2 classes, not necessarily 2. But when classes have labels clearly categorized, you make use of supervised learning. When you are not sure about how many classes are there, whether there are classes or not, you go for unsupervised, you are exploring. So basically, unsupervised learning is again exploring the patterns in the data. And supervised learning is trying to basically model the data. These are different names of supervised and unsupervised learning algorithms. I'm not reading them all. Oh, the names are here, sorry, but I'm not reading them all. And now I talk about my ongoing research. Well, this session is being live streamed. And since you are sitting here face to face, you have an advantage of asking questions as I speak. But any of the participants,
Sure.
yeah,
Three.
there are three.
Yes. How statistics focuses on past, data science focuses on future.
Okay, one is there is an eco, another is how statistics focuses on past.
Yeah, that's the question. The other thing is logistic.
Ramajan, have I answered your question because I discussed this, or should I repeat it one more time?
Yes. Yes.
Oh, okay, thank you. So now, thank you. All right, so now I talk about my ongoing research. It is classifying an individual as employed or unemployed on the basis of individual characteristics. You will have lots of questions because you have background in economics, and this will actually challenge the conventional thinking. I made use of data from TLFS 1920. Now, why 1920? Because I started working sometime back, and the data which have been published recently, there are some minor but some changes in some additional variables that are added to the latest survey, 2 or 3 variables, and then I would have to, look into the structure and then again extract the data, and then a lot of things have to be done for merging and other things. So right now I'm using only this, but eventually I plan to include 18, 19, 19, 20, 2021. All 3 years.
17, 18.
17, 18 is there? Okay. Thank you for the information. I will include that as well. So data sets of household characteristics and personal details are merged after subsetting for relevant features. Okay. Now you should be having questions that why I am saying relevant features, because I said everything that is there, put it in. Yeah, but relevant means I'm talking about employed or unemployed. At the moment, I'm making use of principal activity status, usual principal activity status. Now there are data on daily activity status also, so I have to exclude that. And that is what I mean by relevant. So I'm not considering daily activity, I'm considering only the last 365 days. The relevant features, other than that, whatever was available, worked out only to household size, household type, religion, social group, and this is what I said, household usual monthly consumption expenditure, and then you have sex, age, marital status, general education level, technical education level, years in formal education. See, here you will see that this could have multiple inheritance. Years in formal education and general education level could have multiple. We will see that. Outcome is employment status, employed or unemployed. Stop. Okay, that works. Fine. Again, domain knowledge is important. I thought, why should I use only 15 to 59 years? Why not include everyone? But no, there is some training in economics that prevents me to do that. So I subsetted it for 15 to 59 years. So this will happen with you as well. When you have the domain knowledge and you are making use of the data, this will happen with you even after getting in this data science field. But it happens with me as well. So I included only those in 15 to 59 years of age group. Of course, I had a reason for doing this. What if I come across a person who is 12 years old, all other characteristics are given to me, and my model says that he can be employed. Legally, I can't employ him. Legally, he cannot be employed, and therefore, I have excluded that in the model, that from the model. Yes. Fine. Data further excluded for those who are not in labor force. Again, domain knowledge. And dummies created for all these categorical variables, this categorical variables.
Excluding people those are not in the labor force, you can include also even if their age group is.
I checked, and there are people who are, there are more on the higher side, people working at the age of 65, 69, and so on. But yeah, they could be included. Well, there is a proposal for all of you sitting over here. Anyone who wants to work on this, write to me. And we are going to do some experiments. And I do not commit anything, but if we come up with something really publishable, you could be one of the co-authors. So, yeah, this household size is a category, not household size, but household type is a categorical variable. So, converted those into dummies, each category 0 and 1. Okay, you know what is a dummy variable, so no need to explain. But dummies are created for categorical variables. And then the total features now work out to 57. Features, the independent variables or the predictors or whatever you can say. They work out to 57, including the features which are measured on continuous scale like age. Not all algorithms can handle missing values. And missing values are just 12, so I decided to remove it. The sample size now works out to 1,49,759, and I've split the training and test sets into 70% training, 30% test. I've worked on Python. Binary logistic regression, intuitive. There are two classes. You have to, identify the odds of a person being employed or unemployed. So simple, binary logistic regression. So binary logistic regression has a sigmoid function, but then I'm imposing a penalty. If you misclassify, I'll see to it that you don't misclassify. So I'm imposing a penalty for the L2 penalty. And what is this L2 penalty? L2 penalty is basically you are trying to kind of minimize this. You are tuning the parameter lambda where your j theta, the penalty function is alpha k theta squared. What is your alpha k? You may call it beta, whatever the coefficients. So you're trying to minimize the sum of alpha k beta, alpha or beta, whatever you may call it, theta squared. And on the basis of that, you are estimating this lambda. There are two types of regressions you might have heard of: ridge regression and lasso. Have you heard this term? Okay. So ridge regression basically minimizes the coefficients which are the parameters for which the coefficients are kind of not so significant, whereas lasso turns it completely to 0. L2 is ridge regression, L1 is lasso and L2 is ridge. So I have used L2 as the penalty for this. L1 is better, but I was getting some errors and they are yet to be sorted. Eventually, I want to make use of it because LASSO is more efficient. It just eliminates all the things that are not required. Have a look at this. Keep this figure in your mind because on the basis of this, I'm going to ask you a question later on. Fine. Should I move to the next slide? Focus more on the right hand side. That's simpler to remember. 1 is employed, 0 is unemployed. Okay. Should I move on? Fine. Now I have a confusion matrix on the basis of running binary logistic regression. What is the confusion matrix? A confusion matrix on its x-axis has actual values, zeros and ones. X-axis 0, unemployed, 1, employed. Y-axis 1, employed, 0, unemployed. Okay. So 1 and 1, 41,821 are correctly classified as employed. Very good number. But those who are unemployed, only 35 are correctly classified. So what I did was, I applied a feature selection technique. I said, I don't want all these 57 categories. Use only those categories which are relevant. And you select the categories whichever are relevant. You select the variables whichever are relevant. So binary logistic regression with recursive feature elimination. So this is what we call in econometrics is the parsimonious model. Compared to the first one, this is a parsimonious model. It has less number of features. And the predictive power is better for unemployed and worse for employed. Compared to this, if you have to select from this two, which one would you go for? Right hand side because that has more accuracy power. And if you have calculated the accuracy on the basis of whatever, I admire your mental mathematical ability. But your answer is correct. So what is recursive feature elimination? It constructs the model repeatedly, either after keeping the best performing feature in the model and repeating it, or removing the worst performing model from the worst performing feature from the model and then again repeating it. So the goal of RFA is to give a parsimonious model, as I said. And yeah, accuracy is higher by 0.004. So you're right, accuracy is higher. But there are these three more demons over here. Monsters, precision, recall, and F1. F1 is the geometric mean of precision and recall. Okay. So if you're not sure about whether you want to make use of precision or you want to make use of recall, go for F1. If you're not able to decide, go for F1. But if you are able to decide, or if you want to decide, what is the basis on which you will decide whether you want to go for precision or recall? So all four.
Motivated by saying that we want 97, 90, but still at 93.
Yeah, it's very poor. It is poor.
It doesn't help much.
Not at all. So accuracy is basically the sum of true positives and true negatives. True positive is 1 predicted for 1. True negative is 0 predicted for 0, divided by total predicted. Precision is the count of true positives. So you are focusing on employed people only. So if you are interested in estimating employed people or somebody's chances of being employed, go for a higher precision. But then recall is the count of true positives out of actual positives. So if you want to say about the reliability of the model, go for recall. And therefore you are confused, so you go for that. Right? Doesn't matter. I have answers to this as well. Precision is more relevant in case of a highly imbalanced data set. I've given the answer to the question that I'm going to ask you in the end. And these are the features that are extracted after performing RFP. So broadly, if we see household type, one type of household, two religions, all the three marital status, some 7 or 8 levels of education, and one type of technical education helps in predicting whether a person would be employed. I don't say or not, employed. The chances of a person being employed depends on all these features. And why I'm saying that the chances of a person being employed and not unemployed? There are still very high true positives.
So you cannot contribute anything to the unemployment rate.
Yes, so that is one major limitation of the model that I'm working with now. But I know the solution. I'll tell you the solution later on. So I said, let us apply support vector machines and check. This is another thing which is different from, not that much different from econometrics, because in econometrics we make use of the quadratic terms, and then we make use of logarithms, and then we go for transformations and stuff. Here we just try to say that, okay, let us use a different approach of classification altogether. Support vector machine algorithm is relatively very simple. You feed in the data to your equation. If it works out to 0, it is categorized on one side. If it works out to 1, it is categorized on another side, and it is divided by a line. So support vector machines, okay. Support vector machines is used to define a hyperplane which is divided by a line. On one side of the line are all employed, on the other side of the line are all unemployed. But then you cannot have that precise categorization, so margins are given. We are all conversant with the 95% confidence interval. So 95% margin, it could be 95, it could be more, it could be less, but yeah, there are margins. We call it margins. In econometrics and statistics, we call confidence intervals. They are called margins. Okay. Margins allow the room for borderlining. You are not sure that given the characteristics of a person, whether he would be employed or unemployed. There are clear-cut people who would be employed. Say, if you are holding a master's degree and if you want a job, the chances that you are going to be employed are much higher in comparison with somebody who is just high school or higher secondary pass out. But then if you want to know whether somebody with a graduate degree is, what are the chances of that person being employed? Are you all right? Then there might be chances that it could be on the employed side, it could be on the unemployed side. So these are borderline cases. Borderline cases would be handled by the margins. So, okay, if there is a slight error. But yeah, if you are talking about giving loans to someone, approving someone's mortgage, support vector machines will not be a very good idea to use. Then here I am using another loss function. And loss function here is y is actual and fx is estimated. So if y and fx have the same values, which are true positives or true negatives, there is zero loss. And if they are misclassified, the loss is 1. Of course, this is a continuous function and there are support vector regressions. So it could be from 0 to 1. But here, since we are having only classifications of 2 classes, it could be 0, it could be 1. The penalty could be 0, penalty could be 1. Sorry, the loss could be 0, the loss could be 1. So this is the diagrammatic representation of what I explained. And this is the diagrammatic representation of margins. But apart from, or what is the advantage of using the support vector machine over binary logistic regression? Is that in case of binary logistic regression, you have a fixed sigmoidal function. Here you don't have a fixed function. You can have linear separation, you can have quadratic separation, you can have cubic separation, you can have 4th level polynomial separation, whatever. So for example, this is a cubic function that is fitted.
In the margin, you can use this right in the margins.
No, even the hyperplanes could be separated by a straight line or by,
Yeah, whatever.
Yeah.
Fine.
but even in margins it could be.
Margins, we say that okay on one side or the other side.
Hmm.
So we are saying that even suppose the top side you are talking about triangles and circles.
Hmm.
So even if triangle comes within the margin of the top side, you still consider it to be a problem.
Correctly classified.
Correctly.
Correctly
That's why you darkened it.
Yeah.
But then
So within the margins, whether you have circles or triangles, they are correctly classified.
so how do you distinguish between those two circles which are empty, the darker purple ones?
Circles, these are on the borderline of the margin. So their chances of being correctly classified are higher. The ones within the margin might be correctly classified, might not be correctly classified. But we are assuming it to be correctly classified. So that is the difference. This is the function. You put in the values. If it works out to 0, it's on this side of the hyperplane, otherwise on the other side of the hyperplane. Sorry?
That is classified. Are they like?
You are estimating a regression line basically to divide the hyperplane using this our standard normal regression equation, and you are classifying on the basis of the outcome. Like here they have used b plus w is less than 0. If it is less than 0, they classify it below the line. If it is more than 0, you classify it above the line. That is what they have done. Is this what you are asking?
It's like within that band.
Within that band, you are talking about this figure? Okay. Yeah, the purple color on the triangles which are below the margin are misclassified and the circles above the margin are misclassified. Yeah, that's right. Okay, the question is, do we expect support vector machines to improve? Forget the why. And don't assume that I have asked a question why it means that support vector machine actually improves. The answer could be yes, could be no. So my question is, do we expect SVM to improve the classification, and what is the risk of using SVM over binary logistics? The answer to first question is, it may or may not. Not necessarily it is better than logistic regression, but it has got more flexibility than logistic regression. So there are chances that it could be better, it may not be. Still, flexibility doesn't ensure that it would be better or it would improve the classification. The risk of using SVM over binary logistic regression is oversimplification. One. Secondly, you may end up, in case of binary logistic, you have a fixed sigmoidal function that you are using. Here you have the flexibility of using linear, quadratic, cubic, fourth order polynomial, nth order polynomial, whatever. But the higher polynomial you go for, the chances of overfitting a model, that is, your model is very high on accuracy so far as training set is concerned, but it is very low on accuracy when you apply it on test. That is one major risk of using SVM. Flexibility, where on one hand is helpful, on the other hand, it could also lead to oversimplified model, leading to what is called underfitting, or too much of strict model leading to overfitting. Confusion matrix. Now have a look at it and tell me, is it better than logistic regression or is it worse than logistic regression? Worse? See, first model we outrightly rejected. We rejected the first model. Do you all agree? Or does this make any sense? Rejected. Okay. If you take a look at the second model, these zeros, the unemployed people are better classified compared to the ones with binary logistic regression, so far as I remember.
Yeah, because it was
271 and now it is 275.
Right.
More or less similar. Okay. But slightly better. Slightly means how much slightly better? 937. Sorry, 934. Better or worse? On accuracy, it is performing worse than binary logistic regression. So far, the best model is binary logistic regression with RFP. So far as accuracy is concerned, but so far as precision is concerned, and I would suggest you go ahead with precision at the moment, is 0.937. So SVM is better with RFP. And which is confirmed from this confusion matrix, which classifies 4 more cases better than the binary logistic regression with RFP. Okay. Now, if we look at the coefficients, if we look at the features that are identified which are significant, some 6 types of household types, 1 type of religion, 2 sexes, only 1 marital status, 4 levels of general, 3 levels of general education, 4 levels, and technical education. Slight difference in the model, the features which are extracted from RFP as compared with binary logistic. Okay, so try one more. Random forests. So this is a tree, and when you grow trees randomly, I mean with simple random sampling, becomes a random forest. And then you average the coefficients. Okay, the same question. Do we expect random forest to do better than this case? You are saying yes. Okay. Anyone wants to say no? You want to say no to the first question?
I think the way you have been, from what I understand, you're saying nothing is obligatory.
Yes. So if somebody says yes, anyone can say no as well. But logically, why this is the third one that I use? Because I thought this might improve. Yeah. Why did I think that this might improve? It's because we are running far more regression as compared to what we are running in binary logistic and SVM. So my answer is yes, your answer could be no. And let us see what the results have to say. How many trees should we grow? Any specific number? I'm not sure I've grown 5,000 trees.
I will tell it later because your time is done.
Yeah.
Trade we can. There is this anecdote of how many hats to make.
Mhm.
So one gentleman goes to a tailor, asks for a piece of cloth, can you make a hat for me?
Okay.
Yes. So ease with which the tailor says yes, he thinks that he will take away some of the cloth. Comes back, can you make two? Says yes. Comes back again and again, 10 hats, he's very happy, goes back, I get 10 hats. Then he comes back, the hats are for the finger.
That's
They're
it.
for the finger.
Oh, okay.
And productive labor.
Yeah.
So the
Yeah.
more you do doesn't mean that you
Doesn't mean that it is more efficient. Yeah. Look at the output.
employment has gone down. It is-
Employment prediction has gone down, but at the same time,
Unemployment
unemployment has improved significantly. Huge improvement. And it is sheer because of the repetition of the same thing again and again, trying to see and taking the averages. So now if you, okay, which one would you choose, random forest or random forest with RFP? This is clear cut improvement over the previous two, so we are going with random forest. Okay, but which one of these two? Without RFP, right? That is intuitively correct. Yeah. Intuitively, you would go for RFP without if you are a data scientist, but then your training in economics and statistics, parsimonious models are better. Yeah. So what is the cost that we are paying for the parsimonious model? Hardly any. So far as accuracy is concerned. So far as precision is concerned, 0.001. So okay to go for random forest, but you may choose the random forest model. It's up to you. You have to give the explanation. Fine. And now you see the entire situation changes. Household size matters. Consumer expenditure matters. Now, as we have our training in economics, this would never go into our heads. This is what I began with. So explore why this is happening. Age matters, years of formal education matter, and therefore only general education level 12 is relevant over here. Otherwise, it is the years of formal education that is more relevant than the education level, general education level. And then, yeah, you have, okay. Another limitation of this algorithm is that I have manually selected that there should be 15 features. But it would be good if you let the algorithm select how many features are the best. So we have to work more on penalties. Which model to choose, scores versus confusion matrix. Any improvements still possible? Yes. Yes. So I'm yet to explore neural network algorithm on this data. Also planning to do training and test split of 80-20 and 90-10. K-fold cross validation is to be done. And since the time is running out, I am answering the question. I showed you that picture wherein I told you to remember something.
Employment.
Employment unemployment. Can you quickly tell me what was your first impression on looking at?
The ratio is
30 or 13?
30.
Okay, whatever it is, it could be 30, it could be 13, but I mean, however you calculate it, I don't know, I appreciate that. But the thing is, the percentage of employed people is far higher than the percentage of unemployed people, which means that the data set is imbalanced. And that is the problem that we see in all these classifications. Ideally, both these should be having light colors, not the black color. The correctly classified cases of employed as well as unemployed should both have light colors. Okay. The answer is you will have to use synthetic oversampling minority techniques mode to make the data set balance. Artificially increase the number of unemployed persons using simple random sampling method and then rerun the algorithms so that this problem is sorted. I think it was too much for too many. No, please don't mind it, but I overran my session by half an hour. Sorry.
The class at 6.
Oh, you have a class at 6. So sorry. Thank you for your patient hearing. Thank you for your questions. Thank you for being interactive. Thank you for watching me. Thank you all.
Thank you so much, Smruti. I think it has been, definitely. So some of the students have been exposed to Python last semester.
Okay.
We have one more question.
Machine learning.
Yeah. Interesting. Yeah.
But I have a few questions like really
So we can.
maybe
Let me see.
specific to me or maybe it will be more general.
Better than logistics. Thank you all. Okay, thank you very much.
Thank
Thank you
you.
all for joining us online.
Thank you,
So
everyone.
we'll now close the meeting.
So first of all, like when
Hmm.
you're talking about SPM and non-SPM, right? Supervisor